Hello everyone, welcome to chapter 3. In this chapter, we arrive at probability and information theory, a title that may initially sound abstract, maybe even overly academic, yet in reality points to something deeply human and deeply familiar. You could translate the spirit of this chapter as the science of managing uncertainty. Once you sit with that idea for a moment, you realize that this is not merely a mathematical discipline, but a formalization of how we already think, decide, and act every single day, often without noticing it. We live in an uncertain world. Not everything is 0 or 1, not everything is deterministic, and not everything follows clean rules. When you wake up in the morning, there is no guarantee about what the day will bring, not because the world is chaotic, but because it is complex. Uncertainty comes from nature, from other people, and sometimes from ourselves. Even our own intentions are not always fully known to us. And the name we give to the language of this uncertainty is probability. This is not a poetic exaggeration. Historically, probability emerged precisely because deterministic explanations failed. Classical mechanics promised certainty, but real life resisted it. Human behavior resisted it. Biological systems resisted it. Financial markets resisted it. Probability was not invented because uncertainty was attractive. It was invented because ignoring uncertainty became impossible. Modern artificial intelligence inherits this exact intellectual lineage. Deep learning does not remove uncertainty. It learns how to reason within it. There are actually two ways to look at this field, and understanding the difference helps frame the entire book. The frequentist view treats probability as a frequency. If you flip a coin 1,000 times, the rate of heads is the probability. It is objective. It is about counting. But in deep learning, we often lean toward the Bayesian view. Here, probability is not just a frequency, it is a degree of belief. It is a measure of how confident the model is that the image contains a cat, even if it has only seen that specific image once. This shift from counting frequencies to measuring belief is what allows our models to reason about unique one-off events. It is what allows a doctor to say there is a 40% chance of a diagnosis, not because they have diagnosed this specific patient 100 times, but because their internal model of the world suggests it. In the structure of this book, I like to think of the previous chapter, Linear Algebra, as the skeleton, the rigid structure of matrices and vectors that holds everything together. Probability, on the other hand, is the heart of deep learning. Without it, neural networks would be silent machines performing meaningless transformations. Linear algebra defines how information flows, but probability defines what that information means. It gives semantics to numbers and turns raw computation into belief, confidence, and expectation. Before we dive deeper, let me briefly outline the roadmap of this chapter. The authors organize the ideas around 5 major pillars. First, we learn the basic language, events, distributions, and the rules of dependence. Second, we introduce the random variable, the bridge between reality and math. Third, we cover expectation and variance, the summary statistics of uncertainty. Fourth, we explore the zoo of common distributions, the building blocks like Gaussian, Bernoulli, and Laplace. And finally, we enter information theory, the science of measuring surprise, which gives us our most important loss functions. Let's start with the random variable. A random variable is just a variable that can take on different values randomly. But there is a catch. We must distinguish between discrete and continuous variables because the math behaves very differently for each. A discrete random variable is like a pixel color, a letter in the alphabet, or the roll of a die. It has a finite number of states. We describe it with a probability mass function, or PMF. This is intuitive. The probability of rolling a 1 is 1/6. The sum of all probabilities must equal 1. It is like slicing a cake. The slices must add up to the whole cake. Continuous variables, however, are trickier. Think of the speed of a car or the exact time of day. These values flow smoothly. You cannot list them all. Here we face a paradox. The probability of a continuous variable hitting exactly one specific number, say 5.000000, is technically 0 because there are infinite possibilities. So instead of mass, we use a probability density function, or PDF. Think of this like physical density. A single point has no mass, but if you integrate the density over a small volume, you get mass. In deep learning, we constantly switch between these two worlds, predicting discrete classes like cat or dog, while manipulating continuous weights and activations. Now, let's talk about relationships between variables. This brings us to marginal probability. Imagine you have a table of data about people's age and their shoe size. This is a joint probability distribution. It tells you the probability of someone being 30 years old and wearing size 40 shoes. But what if you just want to know the probability of someone being 30 regardless of their shoes? You simply sum up all the shoe sizes for the age 30. This is called marginalization. It is called that because in the old days, accountants would write these sums in the margins of their ledger books. In deep learning, we often marginalize out the variables we don't care about to focus on the ones we do. This leads to one of the most fundamental ideas in the entire book: conditional probability. Conditional probability means evaluating an event given some new information. The notation is P of y given x. The vertical bar stands for given. A classic real-world example is medical testing. Suppose a disease is rare, only 1% of people have it. A test is 99% accurate. If you test positive, are you 99% sure you have the disease? Intuitively, you might say yes, but probability theory says no. Because the disease is so rare, the number of false positives actually overwhelms the true positives. The probability might be closer to 50%. This is the difference between p-test given disease and p-disease given test. Humans instinctively confuse these two. Deep learning models, if trained correctly, do not. They learn the conditional distribution based on the evidence. We can stitch these conditional probabilities together using the chain rule. The chain rule tells us that any complex joint event, like a sentence of 20 words, can be broken down into a sequence of simple steps. The probability of the whole sentence is the probability of the first word times the probability of the second word given the first, times the third given the first two, and so on. This simple rule is the mathematical engine behind modern large language models like GPT. They don't write a whole paragraph at once. They compute the conditional probability of the next token step by step, chaining beliefs together. However, keeping track of everything that happened before is expensive. This is where independence and conditional independence come to save us. Two variables are independent if knowing one tells you nothing about the other. The roll of a die and the price of tea in China are independent. But in AI, we rely on conditional independence. Consider this example. Your shoe size is correlated with your vocabulary. Why? Because babies have small feet and small vocabularies, and adults have big feet and big vocabularies. They are dependent. But if we condition on age, if we already know you are 25 years old, knowing your shoe size no longer tells us anything about your vocabulary. They become conditionally independent. This concept allows us to simplify our models massively. We drop connections in our neural networks because we assume that once we know the features in layer 4, layer 5 doesn't need to look back at layer 3. Now let's move to the statistics that summarize these distributions: expectation and variance. Expectation is simply the average value you would get if you repeated an experiment infinitely. It is the center of gravity of the distribution. In deep learning, our goal is often to minimize the expected error. Variance measures how spread out the values are. Low variance means the model is confident. High variance means it is uncertain or the data is noisy. We also have covariance, which measures how two variables change together. If the covariance is high, it means when one variable goes up, the other tends to go up. This is crucial for understanding how features in data relate. If two pixels in an image always turn black together, they have high covariance, and the model learns they are part of the same edge or shape. The chapter then introduces us to a zoo of common probability distributions. You need to know these because they are the predefined templates we use to model the world. First, the Bernoulli distribution. This is the coin flip. It deals with a single binary variable, 0 or 1. Every time you build a binary classifier, spam versus not spam, the output layer is effectively modeling a Bernoulli distribution. Second, the multi-Nulli distribution. This is rolling a dice with k sides. It models categorical data. When the network predicts which of 1,000 objects is in an image, it is outputting a multi-Nulli distribution. But the king of all distributions is the Gaussian, or normal distribution. You know it as the bell curve. Why is the Gaussian so important? Why do we use it for initializing weights, for adding noise, and for regression targets? The answer lies in the central limit theorem. This theorem states that the sum of many independent random variables naturally converges to a Gaussian distribution. Since noise in the real world is the sum of millions of tiny causes, thermal atoms vibrating, sensor errors, photon scattering, that noise tends to be Gaussian. Therefore, choosing the Gaussian is not just convenient, it is the most honest assumption we can make about noise when we lack other information. It assumes the least amount of structure. We also have the exponential and Laplace distributions. These are sharp, peaked distributions. They are vital in deep learning for a specific reason: regularization. When we want our neural networks to be sparse, meaning most of their weights are zero, we add a penalty that mathematically forces the weights to follow a Laplace distribution. This is known as L1 regularization. It's a beautiful connection. A specific mathematical penalty in optimization is actually just a specific prior belief in probability. There is one more weird distribution mentioned, the Dirac delta. Imagine a Gaussian distribution that gets thinner and taller, until it is infinitely thin and infinitely tall at exactly 1 point. That is the Dirac delta. Why do we need this theoretical monster? Because conceptually, your training data is a set of specific single points. To describe your data set mathematically as a probability distribution, we say it is a collection of Dirac deltas centered on your data points. This is called the empirical distribution. When we train a model, we are trying to minimize the distance between the model's smooth distribution and this sharp, spiky empirical distribution. Let's verify our understanding of the tools we use to manipulate these probabilities. The book highlights the sigmoid and soft plus functions. The logistic sigmoid takes any real number, from negative infinity to positive infinity, and squashes it gracefully into the range 0 to 1. This effectively turns a raw score into a probability. It is the gatekeeper of belief. The soft plus function is a smooth version of the ReLU, rectified linear unit. It is useful because it ensures a number is always positive, which is necessary when we are predicting things like variance or standard deviation, which mathematically cannot be negative. Now we enter the second half of the chapter, information theory. This field was founded by Claude Shannon to solve a communication problem. How much data can you push through a wire? But in deep learning, we use it to measure structure and similarity. The core unit is entropy. Entropy measures uncertainty. Imagine a fair coin. It has a 50-50 chance. This is maximum uncertainty and thus maximum entropy. Now imagine a rigged coin that lands on heads 99% of the time. This has very low uncertainty. You are almost never surprised. Low surprise means low entropy. Shannon's insight was that information is surprise. If I tell you the sun rose this morning, that carries almost zero information because it was certain. If I tell you there is a solar eclipse today, that carries high information. We measure this in bits if we use log base 2, or nats if we use the natural log. In deep learning, we mostly use nats. This leads us to the most important formula in training classifiers: cross-entropy. Cross-entropy measures the difference between two probability distributions: the true distribution, the label, this image is a cat, and the predicted distribution, the model. I think it's 70% cat. Minimizing cross-entropy is mathematically equivalent to maximizing the likelihood of the correct class. It is a penalty that grows exponentially as the model makes confident mistakes. If the model says, I am 100% sure this is a dog, but it is actually a cat, the cross-entropy loss goes to infinity. It punishes arrogance. Closely related is the KL divergence, Kullback-Leibler divergence. This measures the extra number of bits needed to encode data from one distribution using a code designed for another. A crucial property of KL divergence is that it is asymmetric. The distance from A to B is not the same as from B to A. Think of it like language. It might be easy to translate technical English into simple English, low loss, but very hard to translate simple English back into technical English, high loss. In variational autoencoders and generative models, choosing which direction of KL divergence to minimize is a major design decision that affects whether the model produces sharp, realistic images or blurry, safe averages. Most loss functions in deep learning measure differences between distributions. That sentence from the book is the key. Whether you are doing classification, cross-entropy, regression, mean-squared error, which assumes Gaussian noise, or GANs, Jensen-Shannon divergence, you are always trying to push the model's internal distribution of beliefs closer to the data's distribution of reality. Finally, the chapter discusses structured probabilistic models. Real-world AI problems involve thousands or millions of variables. Representing the full joint table is impossible. It would be larger than the universe. So we use graphs. Directed models or Bayesian networks use arrows to show causality. A causes B, B causes C. This is easy to sample from. You start at the top and work your way down. This is called ancestral sampling. Undirected models like Markov random fields just show connections. A and B are related, like pixels in an image, but neither causes the other. They just have an affinity. These are harder to sample from, but easier to define for things like images. Deep learning has largely moved toward methods that allow us to learn these structures implicitly, but the language of graphical models allows us to design the architectures, like transformers or attention mechanisms, that decide which parts of the data should look at which other parts. There is a small technical warning in the chapter about transforming continuous distributions. If you have a function y equals f of x and you transform a probability density, you cannot just plug in the formula. You must multiply by the Jacobian of the inverse transformation. Why? Imagine painting a balloon. The paint has a certain density. If you stretch the balloon, transform the space, the paint spreads out, the density decreases. You must account for this change in volume. This concept is the mathematical foundation of normalizing flows, a powerful class of modern generative models that can learn complex densities by stretching and squeezing simple Gaussian noise. By the end of this chapter, something fundamental changes in how you view AI. You stop thinking of models as simple prediction machines that output a single answer. You start seeing them as distribution learners. Learning means aligning internal belief with external reality. Overfitting means your internal belief is too sharp, spiked on the training data, like a Dirac delta. Underfitting means your belief is too broad and vague, high entropy. The goal is a calibrated distribution that captures the true uncertainty of the world. And this leads to a final reflection, echoing the sentiment of the sentences we reviewed. Artificial intelligence is not a wisdom machine. It is a large-scale uncertainty management system. It computes probabilities at scale. And when scale becomes massive enough, what emerges begins to resemble intelligence. But unlike human intuition, which is often riddled with logical fallacies, these models, ideally, follow the strict calculus of probability. They don't fall for the gambler's fallacy. They update their priors using Bayes' rule. In a way, they are more rational than we are, provided their data is clean. Probability is the language of uncertainty. Information theory is the science of measuring it. Deep learning uses both to turn the world into numbers and extract meaning from them. In the next chapter, we move to numerical computation, where we learn how to actually implement these high-level ideas on a computer without running into errors. But remember this: entropy, cross-entropy, and the Gaussian distribution form the mental core of modern deep learning practice. You will see them in almost every paper you read from now on. I am Sadi, Evren, Seker. I share the core knowledge that truly matters in the age of artificial intelligence. See you in the next chapter.